Has anybody ever tried to rate a tornado?
And I would like to know why you can never get to the end of a rainbow.
What's the worst disaster in Iowa?
What are your top 3 movies that involve weather?
Welcome to Weathered Questions, where we answer the questions on your radar.
Welcome on in, everyone, to Weathered Questions, the podcast where we answer the meteorology questions on your radar. Also, welcome to the month of May of 2026. We thank you for listening, your positive feedback, your questions, and telling clearly your friends and family about this, because we've had several thousand downloads since we started this program. So thank you very much for all of that. We encourage you to continue to submit your questions. There are no dumb ones. We want to know what's on your radar. We want to know what's on your mind about weather. You can email us your questions to weatheredquestions@gmail.com to join in on the conversation. The cloud of the day continues to be more and more of a challenge, Jan, because we're running out of clouds. So instead, here we're going to tackle kind of a broad brush topic on clouds. Mm-hmm. So the general question here is clouds. Can you look at them and know what the weather will be? Your thoughts?
Yeah, I love this. And we've both been asked this one before many times. Like, yeah, do you really need all your fancy tools? Can't you just, look at stuff? And to a degree, you can. Now, I cannot look out my window right now and tell you what it's going to be like next Saturday. Mind you, I'm recording several days ahead of Saturday at this point. If it's Saturday where you are, I probably could. But I can't forecast several days in advance, right? I can do a couple hours, maybe, up to a day, depending on what kind of thing we're looking at here. So the long and short of it is, yeah, we can. There's a couple different ones. We've talked about fair weather cumulus clouds before. And generally, you're going to have fair weather with those. That's why the name comes in.
Nice weather. Yeah.
Yeah. Now a cumulonimbus cloud, if that's heading your way, it's a pretty good indication. You can see, the towering feature of that. You can see, the low clouds at the bottom and everything going on, that you're going to have some stormy weather. So again, based on the type of cloud that's moving in, you can expect that specific type of weather. So if you're getting a nimbus cloud of some degree, then you're probably going to be getting rain. So that's kind of the broad brush answer. If you want to get into maybe a little bit more specifics, one thing that I like to look at, especially I would relate this to a stratus layer. If you can see, generally speaking, the definition in the clouds, where you can kind of pick clouds apart a little bit, generally, I would say it's going to be more just a cloudy kind of gray day. Whereas if everything is kind of muddied together and you're not able to see very much definition in those clouds, generally you can expect rain coming very, very soon. So that's one kind of fun little thing that, there's not a specific cloud type for that or anything, but just kind of a general practice that you can look at a little bit. You can also, if you're looking off in the distance, maybe you see a full swath of clouds covering the sky, depending again on other things happening, but you might be able to guess that there's a front moving in, and so that's likely going to bring a change in temperature, as well as potentially some precipitation also, again depending on a couple other things probably too, but a meteorologist would probably be able to have a pretty good indication on that, and somebody who's maybe been around that climate or that weather for a while would maybe be able to also. Kind of a long-winded answer. What do you have to say there, Kai?
I've got a few tricks too that I've used over the years. One of them is if you start seeing a layer generally of clouds begin to form, and within that it kind of has a definitive flat layer, not like a flat bottom like a cumulus cloud, but almost like a flat, like a ruler is in the air. And you start to see what looks like the top of like castle turrets starting to show up, like little spikes. That's an indication that we have what we call warm air advection aloft, and it's unstable. And 9 times out of 10, when I see that stuff, we actually call those alto. It's an altocumulus cloud. It's a different family though. It's the Castellanus cloud. So they named it that because it looks like castle turrets. You're probably 2 or 3 hours out from having showers pop up on the radar. And that's a sign of mid-level instability. Another fun little cloud tool, and actually it's interesting that this is even coming up because I had this happen about a week and a half ago. I had a family member over. They were curious how warm it was going to be for soccer that afternoon. And I said, probably low 70s. This was probably 11:30. They said, it's already 68. I said, I know. So why would we all of a sudden just stop warming? Well, it's because a field of cumulus clouds popped up. And whenever you start to see cumulus clouds in those fair weather situations, it's been my experience that you are only going to warm about 5 more degrees. So if you're 68 at 11 and the cumulus clouds start popping, it was great to see how fast it warmed all morning, but you're probably going to start leveling out now.
Yep.
You might squeeze 5 more degrees out once you get to that level. And try it this summer. Just think about it. If you start seeing a bunch of cumulus clouds form, look at the temperature. Now, this is absent, a huge cold front or a huge warm front. This is just a fair weather day where it's fairly clear and calm. That's how that works. And the physics behind it is now you've pretty much mixed out the atmosphere as much as you can. And you've mixed it enough that we're starting to see what we call lift in the area. And just the heating of the day is causing that. And then pop, 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 pop. These little cumulus clouds go off. And then you're pretty much done warming for the day. Even though you've got 8 hours of daylight left, you're done. And sure enough, the temperature just flatlines.
Yep.
So that's another fun trick and technique. If you've ever seen a wall of cirrus clouds start piling up in the western sky, good chance something's causing that. Cirrus clouds don't pile up for no reason. So check your radar. There might be a storm 100 miles away. I've seen storms in western Iowa blow off with cirrus, and you can see them by Davenport. 200 miles away, you can start to see the cirrus coming off of some of these larger thunderstorms. So if that ever starts happening, that's a great takeaway that something's maybe a little ripple in the force, if you will.
Yeah.
That's all I can think of right now. But those are the techniques that I actually use and rely on, and they work well. They really do. They work nice.
Yeah. But again, that only gets you out a couple hours,
It does.
maybe to the end of the day kind of
Top
situation.
6 to 8 hours tops. Yeah.
We're not using that to build a 7-day forecast. That takes a lot more and gets us into our next question quite nicely, I might add. That question is, what tools does a meteorologist use to accurately predict the weather, and how do they use them? For example, what is like a Doppler radar and stuff like that? Like, what are these tools that we're always talking about, but we just kind of gloss over?
I would argue that we actually have a fair amount of meteorologists who may not even know how all these work that are currently in the field right now. And I'll just go through my whole forecast process that I used to use when I was on TV. It'll only take me 2 minutes, and we'll get through the entire thing. So first, you got to start off with a snapshot. Are the models actually capturing things well? So you look at all of your current conditions, which typically come from airports at night, because I always worked in the night into the early morning. And then you cross-check that with, how's my satellite imagery looking? Is my radar picking up on anything tonight? A lot of times what people don't realize is the radar lights up quite often at night because of something called ground clutter. What'll happen is the radar beam comes out of the radar, and because the Earth is round, and because we usually have what's called an inversion in the atmosphere, meaning that we're cooler down near the ground than maybe a few thousand feet up, the beam actually hits that and can go back down to the ground. So sometimes we can see traffic showing up, or buildings, or wind farms are especially a pain in the neck to try and sort out in the middle of the night, because you think it's storms until you animate them and realize they're not moving. So you cross-check your radar and your satellite, link that up with some of the latest model data that you have. I always start off with some of the short-term ones, because if there's any part of the forecast we want to get right, it's the short term. The long term, I think people realize, is going to tweak. But that first 24 hours, you really want to put a lot of your effort in there. So high-resolution modeling, radar, satellite, try and link all that up. And then, of course, the final thing is a little bit of gut. Do these models actually have a right handle on this? This model is shooting a warm front through here. It looks like it should be closer to 90, but the models are only going with 81. Why? And then you have to interrogate that a little bit and go, what? It should be hotter than this. Why is it not going higher? And then you figure it out. And then this, Jan, takes us back as to why we go to college to do this.
Mm-hmm.
Because undoubtedly, under the hood of every model is more math than anybody ever wants to see in their life. Like, there is so much math in there about how these equations work and how they're governed and what the assumptions are. So that was my typical process. If you have a weather balloon, use it. Use all the data you possibly can to your advantage. Radar, though, by far, especially in the short term, is one of the most powerful tools we've got to detect anything that's really dangerous or inconvenient to your day. Because let's face it, if it's sunny and 80 versus sunny and 60 versus sunny and 70, aside from how you dress, nobody cares. They don't care.
True.
If there's a thunderstorm brewing, now they care. Now their garage sale's ruined. Soccer game's ruined. Or maybe they adjust their day. Seeing radar light up, I'm going to mow the yard now to get some fresh rain on it later. So radar is by far one of the coolest upgrades we've had. Satellite is right there with it too. The stuff we can see on satellite now is so much better than what I had in college, for sure. No, it's good stuff.
We can see. So I mean, you can do drought analysis from space with the satellites we have now, right? It's not just a general picture of, oh, clouds are present, clouds are not present, that it maybe used to be, but there are so many different tools within satellite themselves. You can have infrared that shows you how high up or how cold those cloud tops are, which essentially is how high up they are. You have different layers basically of that satellite that you can utilize to help you with your forecasting, nowcasting, and forecasting alike, similar to that radar, how that has changed, right? We've had dual pole radar now since, is it 2012? 2013?
2012. Okay. Some sites even had it, I believe, in 2010.
Yeah.
But 2012 seems to be the understood cutoff. Yeah.
Yep. So, and we've talked about it before, right? Radar is radar. There are very few personal radars or specific TV station radars anymore. Generally, everyone is using the National Weather Service radar. It's the same radar, whether it's blue or green on whatever weather app or station you're watching. It's the same data, and it's dual pole, which basically means that that radar is sending out two beams, a horizontal and a vertical. And that's basically telling us, instead of just rain is present, which it used to be doing, or something is present, now we can tell things about the shape of that. So we can see, is it something that is maybe more round and tumbling, which, guess what? Raindrops aren't like that. Nope. Raindrops generally look like a hamburger bun as they're falling because of air resistance. And so we can look at the shape and see that horizontal versus vertical and tell maybe what type of precipitation is falling. We can tell how similar things are together. So if it's a raindrop mixed with bigger raindrops mixed with a 2x4, that right. is something that we can see on a part of dual pole radar called correlation coefficient, and that's something that we would look for if we're potentially trying to track a tornado. Yep. Whereas if you have a bunch of raindrops that are all similar in size together, just rain, it's going to show up differently, not a problem, at least in terms of if we're looking for a tornado. So there's lots of different parts of radar. It's not as simple as just what most people are pulling up on their weather app. There is a lot more detail to it, and many meteorologists or fellow weather geeks and nerds and stuff will have a higher, better tool than just a general one-layer radar that shows reflectivity, which is that kind of base radar that everybody somewhat knows about.
And let's not forget the advancement in computing power.
Absolutely.
We can do all this stuff now in so little time. When I first started in television, what we would do is I would set frame 1 of the surface map, and I would set frame 300 of the surface map, and I would render it. And that's the thing that shows the cold and warm fronts flying across the screen. And it was a 20-minute job. And so that was for one graphic.
Just to show it moving one progression.
just to
Yeah.
show it moving. And so then at that point, we'd go out in the newsroom, we'd talk at 3 a.m. and go make a pot of coffee and make sure everybody's taken care of. And then you get back to the computer and all right, that's done. And then you realize I drew it the wrong way. You'd have to redo it. A lot of people right now don't realize that every one of these smooth rendered graphics you see on television, it's instant now.
Yeah.
You can do it in a commercial break.
Well,
and
what a
still
lot
have
of people
time.
also don't realize is that the meteorologists are making those themselves.
Yes,
we don't
they are.
have a producing team doing that
Mhm.
for us. It's usually a one-man band.
You got that right. That's for sure.
Yeah. And even if your station has 5 meteorologists on staff, usually they're not all there at the same time. Rarely are they there overlapping. And so, yes, again, one-man band.
Yep. The to-do lists are long and getting longer for sure.
Well, hopefully that answered that a little bit. If you have further questions on that one, let us know. But we're going to get into something kind of related to radar and what we were just talking about a little bit. Why does it rain different? And they give an example of like a drizzle versus a downpour. Why does it rain different?
Good question. As cool as it would be to have a big, huge yellow blob like it shows on Futurecast to come through and just all of a sudden rain, all of a sudden stop, just like our faucet, that's not how raindrops are formed. We have to have a moisture source, number one. And then we need to have a way to get the moisture, what we call condensed, out. So we hear about this with the water cycle, right? We've got runoff. We've got our water source near the ground. We have evaporation. Then it condenses into precipitation, and then it falls, and it goes back. And that's the circle of water. So if you've got a drizzly situation, there may be just enough cool air around to condense it. You could liken this maybe to get a can of soda out of the fridge or a can of sparkling water, a can of something, and set it out on kind of a non-humid day. Make sure the dew point's at least 40 degrees. Put it outside. You might get a very narrow little film around the outside. Very small drops. Just enough that your hand is damp when you touch it. It's condensing into small drops. Why? Because the moisture is very limited and really hasn't done much. Take that same can at that same temperature and put it outside in the middle of a July afternoon. Dew point of 75 degrees. You will have large drops running down that thing. What changed? The amount of moisture in our atmosphere changed. But then number two, if we were to actually make this happen in our world, you take that warm air down near the ground. Let's say a cold front comes in and you lift it. Now you have magnitudes more moisture being lifted in our atmosphere higher and condensing more. And what does that mean? More and more and more water droplets are going to be rinsed out or condensed out. And what happens is they will go through their production processes, which is a whole unit in microphysics that we're not going to even touch in this program. But they will essentially bump into each other and they might merge and they might get a little bit bigger and they might grow as they fall. They might scavenge up some other ones as they fall out and you get these big raindrops. And then radar sees that as, oh, there's more stuff in our atmosphere now for my radar beam to bounce off of. And we call that reflectivity. So now you might see yellow or red showing up because there's a bunch of stuff in the air that's coming back to the radar. That's heavy rain. If it's drizzle, it might be so light the radar doesn't even know it's there. And raindrops, as you said earlier, super, super light rain are very small drops. Heavy rain are big drops, big flat ones. Drizzle drops are almost pure circles. You know why? Because they're almost always just suspended. They barely fall at any sort of rate. You might notice it if you go run an errand when it's drizzling. You're going to notice it more when you're driving than when you're walking into the store. Because now you're actually taking these small drops and smacking them on your windshield at 35 miles an hour, as opposed to them barely just softly, willfully falling on you. So that's the biggest.
The same reason why you shouldn't run in the rain, because you actually get more wet if you run.
Thank you, Mythbusters. Yes, I like that. But it's true, though. And that's kind of the biggest difference is the process. How much moisture do you have, number one? But how much is that air being lifted and forced upward? That's the big thing is, are you forcing something up? Either is low pressure coming by and lifting the air, or is the front coming by to lift and squeeze that moisture out? I was taught a long time ago, it's kind of like moisture in a dish rag. If you leave it alone in the sink, it's not going nowhere. If you put some force on it and squeeze it and wring it out, now you're getting all the moisture out. And that's essentially what the atmosphere is doing on a very warm, humid day. Otherwise, it'd rain all the time everywhere. So there has to be a mechanism to force that water out. And that's the process to do it.
It's a really good comparison. I like that.
There you go. So we can keep going on this, and let's start moving into stuff that's, actually fairly common lately and fairly hazardous. So when we go and take that next step, how do you know when a severe storm will produce hail while others will have strong wind or tornadoes?
Yeah, so we're still talking kind of about our atmospheric ingredients here, right? But basically what it comes down to is these are different types of weather at their core. And so we need different ingredients for each of these. Hail needs a very strong updraft in order to be able to form well, whereas wind tornadoes generally are going to have maybe a stronger downdraft for. So those are, two kind of nuances that you would have differences. We're also looking though at, many things, but we've talked a little bit about the energy needed for severe storms, that CAPE, that's basically how much energy, how much energy is in the atmosphere. We'll just leave it at energy, keeping things simple, right? How much energy is available for those storms to fire off of. Wind shear, another kind of term that we've talked about a little bit before, and kind of, seemingly fictitious, but basically how that wind speed and direction are changing as you go up through the atmosphere. That will play a role. And so all of those things, we're looking at each of those different ingredients on their own to be able to give us an indication of, okay, we have a updraft with this storm, stronger updraft, higher moisture content, all of those things may play into, okay, we're going to have a big hailstorm here. Whereas if we have wind shear, if wind shear is too light, maybe we won't be able to get tornadoes to form. If wind shear is too strong, maybe we won't get tornadoes to form. As powerful and windy as tornadoes are, they are very persnickety and need a very specific amount right in that kind of middle layer, or middle range, I guess, of how much wind shear they actually need. If you have too much, they're actually just going to kind of rip themselves apart. The storms just can't sustain themselves. If you have too little, well, you're probably just not going to have severe storms. You're just going to have maybe a quick little pop-up shower or storm here and there, and then it's just going to kind of kill itself. Basically, it rains on top of itself and kills itself. So a lot of different ingredients that we're looking at, but all of these are things that we see present in severe storms. It's just which of those ingredients are at the higher amount and what type of thing you're going to get. It's just like if you're making a cake versus cookies, you're probably going to use flour, you're probably going to use sugar, you're probably going to use eggs and butter and, all of the same things, but it's the amount that you're putting them in and the order that you're putting them in that is going to matter of what your end result is, if you're going to get a hail cookie or a tornado cake.
That's true. I like that. The one big tactic I use, this is a fun little fact, that at least half of a thunderstorm is below freezing. And in some of the worst, you can have 70 to 80% of that storm below the temperature of freezing. So even though it's hot and humid down near the ground, there's a whole lot of that storm that's actually well below freezing. Yeah. And there are different layers that we look at. We look at the freezing level. We look at where we're at minus 20 Celsius, minus 30 Celsius. Up in there, hail really starts to grow nicely and efficiently. Mm-hmm. One of the tactics I look for is, do I see really high levels of reflectivity? Do I see yellow and red when I tilt up in the radar? If we're at minus 20 or colder and we're still that reflective, what does that tell me? Those aren't raindrops no more. Those are now chunks of ice colliding with each other.
Yep.
They could also be one other thing, which I'm going to tie our last question into this too, because hail has layers sometimes. Here's why. So when we're up there in that cold environment, we have a mixture now, don't we, of ice and what we call supercooled water. I know you've got a great experiment for this, Jan, that we'll have to talk about another episode, about how you can get supercooled water and all of a sudden you just flick it with your finger.
Oh, yeah, that's a fun one.
And it just solidifies. It's like, the water is super cold. So when the hailstones are growing, if they're growing with other hailstones kind of colliding into them and sticking to them, you're going to see rings start forming around these things. And if it's a cloudy ring, then existing ice particles were hitting the stone. If it's a clear ring, then it was supercooled water hitting the stone and making a nice clear layer around it. And what happens is the updrafts that you were talking about and the downdrafts you're talking about, as soon as the hailstone gets too heavy for that updraft, what do you suppose happens? It falls.
Yep.
And it doesn't always fall straight down. It might be, off by a third of a mile or a half a mile or whatever the trajectory is in the storm.
Because there's other wind, right?
There's
side
other
wind
but
instead
I'll
of
tell
just
you,
updraft wind.
some of the largest hailstones in that really awesome environment, they'll fall really close to that updraft because they've been growing there the longest and they're the largest, which means the wind has a whole lot less effect on a large hailstone because it's massive, as opposed to a pea-sized hailstone, which you could take a handful of frozen peas and throw them out the window. They're going to go everywhere. So that's one of the reasons there.
There's
about
your experiment
hail.
from Kai.
There it is.
Throw a handful of peas out
But
the
that's
window.
why hail has layers, is just the way that it's growing and how many trips it takes up in the storm. How many layers of refreezing does it go through? It's really cool science, actually. And if you ever get a hailstone and break it apart, you're going to probably see that, especially if it's a 1 inch or greater stone, most likely.
Yep, it is pretty cool to see, especially when you get those cloudy versus clear layers kind of alternating.
Oh,
and
yeah. It's cool.
you can see the layers
Yep.
really clearly, like it's an onion or something. It is.
Yeah, you
it
can
is really
visualize how the stone actually grew in the storm.
Mhm.
And that's neat to see. And then whenever you get reports of hailstones, if you get a 1 inch hailstone at your house, please report it to somebody so that the Weather Service knows. It'll help them with future warnings on that same storm cell. So it's all
Absolutely.
good stuff.
Yep. Alrighty, that takes us to the end of another episode. Thank you again for joining us, listening, asking your questions. A lot of listener questions today. So we'd love to get those. And remember that you can email your questions in to weatheredquestions@gmail.com to join in on the conversation and let us know what's on your radar. Until next time, stay safe.